this language was for it to be executed on computational devices. So he essentially like predicted artificial intelligence in the 1650s and began starting to write it. And then if you come to Bertrand Russell, who was actually Wittgenstein's teacher, which is really neat, he comes in a little bit later, but Bertrand Russell critiqued, Bertrand Russell critiqued Leibniz's Principia Mathematica, the book, in 1908, and in doing so created what's called type theory, which was also a huge response to Friese's naive set theory. And that was, it's a continuation of ontology and the shaping, it's talking about the way that we interact with the world and the way that we understand the world and the systems and the schemas and the ways that we use to do that. And sets were one explanation. So there's a set of all apples, a set of all oranges, there's a set of all people with red hair, there's a set of all people with red hair who are dead. Like, any set is basically posited forward and it's brought into being in a sense. But there's a lot of issues with that, and Russell sort of brought a lot of those to the forefront, and the main response, one other thing called Russell's paradox, which I won't get into, but it's the idea of this hierarchical ordering system, and that really changed a lot, and it really is effective and influential on computing sciences and even modern-day programming languages. They all operate off of something called object-oriented programming principles, which is essentially just a hierarchical ordering of class types within a program structure, which is very much influenced very directly. They even have there's so many types of type theory now, ironically enough. But
types of type
yeah,
theory.
which is really neat. And so that sort of coming of age in the early 1900s really started to found computational sciences and developments of programming languages through these formal logical derivations in these systems that we're doing. Even the syntax is highly prevalent when you get into digital circuits and stuff today, the same exact syntax. We even use truth tables, except they're zeros and ones instead of T's and F's. But so as we move forward, which is really cool, we get into so the 1940s and 50s, we start to have this really big turning point with Alan Turing, who is one of the most interesting people in history without a doubt.
Turing is the turning point.
Yeah, Turing is the turning point. But he was brilliant. He was actually the person who cracked the Nazi code that helped end World War II. Because initially when Germany invaded Poland, one of the key things that helped us win the war is Poland actually captured one of their translation devices. It's this big machine they used to encode their messages, their war messages. They captured that, and they had to actually break it. And Turing was the person who not only broke that and saved so many lives. They used that on D-Day to actually send false messages, so they thought they were storming the beach miles and miles down from where they actually did. And it was one of the reasons the invasion into continental Europe was actually successful. And so not only did he help win World War II, but he founded, and he's credited as the father of modern computer science. And he was eventually put to death because he was also a gay man. So all around, pretty influential, crazy character. But amidst all of that, he also posited what's called strong artificial intelligence. So weak artificial intelligence is demonstrated by your phones and even that toaster. It's pre-written, it follows a script, it demonstrates aspects of intelligence, the ability to use information and data, even apply that in an applicable way. But strong artificial intelligence takes that a step further, and it basically posits the idea that a computer system running the correct program is in itself a mind. Not like a mind, not akin to a mind, but a mind. And that's really revolutionary. And he's credited sort of as the birth of this study of artificial intelligence, but it also resulted in this progression of this idealism called computationalism. And computationalism takes his position and basically exacerbates it. And it creates, as computation essentialism, it follows basically along this metaphor that the wet work of our brain is akin to the hardware of a computer, and the program running on a computer is akin to our mind. And in this way it falls along Cartesian dualism, or in what some authors refer to as the rationalistic tradition. But this idea of Cartesian dualism, that we have a mind that is distinct from our body, this body is this earthly thing, and this mind is entirely different, and yet they are some way related, that was really popular within philosophy up until quite a bit before this point, actually, within the computational development. But computationalism nevertheless ran rampant. It was this huge idea that really took hold within computational sciences and artificial intelligence up until about exactly 1980, when Searle released his paper Minds, Brains, and Programs, which he posited the Chinese room thought experiment. But essentially, he came up with the conclusion, and the very apt one, that syntax does not beget semantics. And so at this point, when we're encoding and telling these computers to do things, they're just following a set of instructions, and they're decoding things, and they're acting this way, and it's representative of weak artificial intelligence. The strong artificial intelligence does not seem to be demonstrated, and he wants to say that it couldn't possibly be. And that seems very extreme to me, but the real drawing point is that you can't get semantics from syntax, that this real meaning of what it means to be an apple is different than an ability to like recognize the word apple or something like that. And so that requires a different type of intelligence. Right. And unfortunately, up until this point within the computing discourse, we lacked the philosophical tools to actually talk about intelligence in a real enough way that the implementation of that in an artificial intelligence field was even remotely possible. And that's going to continue on until we get into the 90s and even 2000s. And one of my main sources is a guy called Paul Jurisch. He wrote this book called Where the Action Is. And it's all about embodied interaction and embodied robotics, which is currently the forefront of artificial intelligence. But what's really cool about it is that it involves a resurgence of phenomenological principles from philosophers like Heidegger and Wittgenstein and Sartre even, and they pull all of those ideas in and these new philosophical mannerisms and ways of speaking about our intelligence and how it interacts with the world. And from that, we get an incredibly different implementation of that knowledge because the base level assumptions have changed and we make huge strides in artificial intelligence. Now, it's still something that is on the cusp that we're working towards, but we have a far better means to do so. And really what my argument was for the actual thing, a lot of it is history and a lot of it is various components, but the actual argument is that if you work in a field that resides or requires philosophical assumptions that inform the practice of that field and inform the implementation of the work that you do within that field, then you have a moral responsibility, even an obligation, to be up to date on what those philosophical assumptions that are informing those things really are. And that did not happen in computing. We fall into this Cartesian tradition or this rationalistic tradition, and for like literally almost 100 years, we're operating off of these Cartesian ideas. Descartes wrote his stuff the same time as Leibniz, about 1650, and it was immediately afterwards that we started moving away from those ideas. Kant already brought us back into the world, and by the time you get to phenomenologists like Husserl, who actually saw himself as a Cartesianist and was trying to articulate phenomenology for mind and for body, and Heidegger, who's maybe my favorite, he's really famous for basically saying, no, we're going to place all of this knowledge, everything that we have within the world, we're never outside of the world, and to deny that there is something external to that is just, we don't have the means or the ability to say that. And that shift really changed intelligence. It wasn't this interaction between this abstract mind and this physical body, but suddenly it was really immersion. We get these ideas like along with Merleau-Ponty, another famous phenomenologist, and he talks about like phantom limb syndromes and walking, and how when you're actually engaged in walking, it's not this cerebral exercise, but it's intelligence that's dispersed throughout your entire body. So when I move my hand, I rely on muscle memory to do so. And those things are trained, those are embedded intelligence, and that is evident in computer systems that we have today. It used to be a centralized computing thing. Everything happened in one place. And then it was connected to these peripheral aspects, these ways of connecting to the world and this embodiment. But as we move into computers today, we actually have processors all over the place. There's computation happening everywhere. So your network card is communicating through your router. It's processing things independently from the central processing unit, which is relying on a graphics card, which has its own processor, which is developing all of these things, and it's integrating with these complicated, intelligent peripheral items like phones and routers that are themselves intelligent. And that type of embodiment was not possible until we actually started to reappraise what intelligence was. We were working off these false assumptions. And once we started incorporating these real ideas like Wittgenstein and even Chomsky to a certain point, this idea of this learned language that we in our brains aren't this infinitely malleable object, but we are set up to learn and experience the world in specific particular ways. As Wittgenstein would say, that like meaning is contained within language. And so suddenly we have these means for actually interacting with meaning, and you have job titles like ontological engineer, which are actual people that work within computing fields today. And they're essentially just really, really complicated versions of Aristotle who are trying to map out the world into a series of meaningful expressions such that we can translate our experience and our intelligence in such a manner that is unique and representative and could be replicated theoretically on a computing system that running the correct program is a mind. And So it's really cool. That I don't know if we can actually attain that necessarily, but I know that we're going to get a lot closer if we continue to refresh those philosophical assumptions and stay true to the roots of our actual.
So where are we going with that? What can it take us to?
Well,
What are the possibilities?
fundamentally, the argument that I'm saying is that basically every field relies on philosophical assumptions to a certain extent, that you have to have an understanding of what it is to be a rational thinking person within a world of complicated meaning and syntax, that what it means to be that kind of entity, or Dasein as Heidegger would call it, is informative and important in relation to whatever you're doing with your life, whether that be art or science or computer science or lumberjacking. Like it doesn't really necessarily matter, but we can't see those strides, and really it's an argument against stagnation, and it's utilitarian to an extent in that regard that I basically hold stagnation as something that we are trying to avoid, and it's something you can very obviously see, and within the literature they point to this entire area of stagnation where we are crippled by the rationalistic tradition within the computing fields, and it's really because of honestly a bit of smugness that we don't have these relations. It's almost like the FBI and the CIA. Like they have their own files on different people, but they don't actually communicate. And so they have these different dependent, isolated intelligence. And yet if they just like share all of their things, they would collectively be a far more better and functioning unit. So you have to get over the bureaucracy to a certain extent within the academia, between these two discourses, but fundamentally the relationship between philosophy and computing not only grounds in a large way both of those discourses within each other historically, but pragmatically in the current day, that we have to be able to rely and replenish and reevaluate our actual philosophical assumptions that inform these types of things. Otherwise, we're just going to fall crippled to stagnation. If I don't constantly, learn and investigate what it means to be intelligent, then if I'm trying to create intelligence, I'm doing myself and the entire discourse a disservice. And so that's essentially what my argument was within the whole thesis. It was pretty dramatic.
And you rolled that in
That was longer than I meant.